This is question 22 from the mid-semester. A sample of 18 ball bearings is selected. For each ball bearing we record the number of revolutions in millimeters until failure. The sample of this data, sample mean is 6.2 and the sample variance is 4.8. Assume that the numbers of revolutions in millions until failure are IID normal random variables. Which of the following is a 95% two-sided confidence interval for the mean number of revolutions until failure based on the data? These questions are all a little bit of a mouthful, so let's try and dissect the information that we've been given and see if we can work out which equation we need to use in order to come up with a test statistic, etc. So given that sample of 18 balls is used, so n is 18. For each ball bearing we record the number of revolutions until failure. Yep. The sample mean of this data is 6.2, so x bar equals 6.2. And the sample variance is 4.8, so that is sigma hat, I think we use for the sample variance. Anyway, the point is it's not the population variance, which is important for which equation we use. Assume that the numbers of revolutions until failure are normal. So that means we can use a t-distribution. We'll talk about that in a minute. Normal random variables. Which of the following is a 95%? So alpha is going to be one take that, 0.05, for the mean number of revolutions until failure based on the correct data. So we're looking for a two-sided confidence interval, and so what that means is we're going to for this prediction we're going to end up with the mean overall, which is mu, is going to be equal to our x bar plus or minus some error, some confidence interval. I forget what we call that. There you go. In the textbook we just use E. So the trick here is just to work out which one of the equations that we can actually use. So just going through the rules, I usually like to start with seeing if we can apply a Z test statistic, or the confidence interval test for a Z statistic, which is equation number 60 in our equation sheet in 2013, and then work down from there. So if we can't do that one, just see if we can use the T statistic, which is the next one down, which is going to be number 72. And so let's have a look at the first one. So can we use a Z statistic? Well, we've got, first of all, the conditions that you need in order to do a test statistic of Z are that it must be a normal population, that you're pulling a normal distribution that underlies the sampling. So don't confuse the sampling distribution with the underlying distribution of the ball bearings. So the ball bearings are normal. That means in theory we could use it, but we also need either to know what the population variance is, and just remember that we are only given the sample variance, and because we don't have that, you need to use a different distribution, which is the t distribution, unless the n happens to be very large, typically greater than 30. So since we don't have those two things, we don't know the variance and the n is only 18, we can't use a Z distribution. So, and you can see in the notes for validity and condition of equation number 60 that you can be replaced by sample standard deviation. And I can see now I've made a mistake here. I've written the sample standard deviation. The variance is squared, and that's an easy one to mess up. So you need the variance of the population or the standard deviation of the sample when n is greater than 30. So we don't meet that condition. Let's check out number 72. So this one's a t distribution. It is normal, so I'm pretty sure we're going to be able to use this, but let's have a look at the conditions given. The validity is when n is greater than 30 or distribution is normal. So the fact that distribution is normal means we can use this. If it was non-normal, then we could still use this as per the central limit theorem. So what that theorem actually says is, and I think it's earlier in this chapter, and if you really want to go back and have a look, but basically the underlying distribution doesn't matter at all if the sample size that you take is big enough each time. It'll still come out in a normal distribution or a t-like distribution. So I'm not going to go into that, but that's all you need to know. If it's a non-normal distribution but the sample size is greater than 30 each time, you can still use this t-distribution. And if it's a underlying normal distribution, then it doesn't matter if n is small, you can still use a t-distribution. So I hope that makes sense. In this case, we're going to use equation number 72, and that's going to tell us that our error, the E, is equal to t of alpha over 2 with n minus 1 degrees of freedom multiplied by our sample standard deviation over root n. So in this case, the t values that we get from our t table in the tables that are given, you always have to be careful what they're actually giving you. In our case, it's a two-tailed t distribution that we're being given, and you can see that when it says the table below gives values of t of alpha over 2, and then in the table itself it lists alpha. So we're looking the second column along of values with the 0.05 at the top, all the way down. N is 18, so we want 17 degrees of freedom, and that's going to be 2.11, and that's multiplied by the root of, remembering that we've been given the variance, so we actually bring the variance under the square root, and it's 4.8 over 18, and that's going to give us 2.11 times root 4.8 divided by 18, 1.09. So now we can find our final answer for our lower limit. I forget what the abbreviation is, so I'm just going to call it lower, is going to be our x bar 6.2, that one, minus 1.09, which equals plus 6.2, 5.11. You can already see we've got the only valid answer, but let's just check, and the high is going to be equal to 6.2 plus 1.09, 6.2 plus 1.09, and that gives us 7.29 as required.